In a previous video, we were given distributions that were standard normal, and then from those standard normal distributions, we used the cumulative normal distribution chart to determine the likelihood of different outcomes. In this section, we will begin with normal distributions, and we're going to learn a method to allow us to transform those into standard normal distributions. Once we've transformed it into a standard normal, then we can do much like what we did in the previous video, using the chart, find the likelihood of different outcomes. Now, what is going to be our method to transform from normal to standard normal? That's going to be something called the z-score, which we see described below. So suppose we have a value x that begins from our normal distribution. So x is normally distributed, but it's not standard normal. Then we can turn it into a standard normal. And one thing I need to mention here is the mean of this normal distribution is mu. The standard deviation of this normal distribution is sigma. Now you know in a standard normal, the mean is 0 and the standard deviation is 1. But as this is just a normal curve, our mean might be something other than 0, our standard deviation is something other than 1. We can then find the z-score, which is standard normal, by taking the x value we began with, here I'll color code this, subtract from that the mean, and from that divide by the standard deviation. Now when you do this, oftentimes you're going to get something with many decimal places. If you look back at our cumulative normal distribution chart, it shows z-scores to 2 decimal places. So for that reasons, always round your z-score to 2 decimal places. Remember, you look at the third decimal place. If it's 5 or greater, round the second place up. If the third decimal place is less than 5, then you round it down. Now we're about to start calculating and using this, but let's just go over a few properties first. The z-score is our standard normal distribution. This is why we go through the effort to do this, because then we can use the cumulative normal distribution chart. We know values below the mean will have a negative score, and that makes sense because if I have a value and I subtract a larger mean, smaller number minus larger number is negative number. Standard deviation is positive, negative divided by positive is negative. So values below the mean will correspond to negative z-scores, and then values above the mean, similarly, larger number minus smaller number is positive, divided by positive number stays positive. They'll have positive z-scores. Now what does a z-score mean? It means how many standard deviations the original value is above or below the mean. Because what we do is we first see how far away are we from the mean with the numerator, and then we say how many standard deviations fit into that difference. That's why we're dividing by sigma. So let's get started with our first example. We're told that we've got a normal population. That's great. We need that first. And the mean, or mu, is 9. The standard deviation, sigma, is 6. What proportion of the population is less than 20? So 20 is our value of interest. It's our x value. I can't just look up 20 in my cumulative normal chart because that chart only applies to standard normal, and this is just a normal population. So the first thing that I'm going to do is I'm going to get my z-score, which will allow me to look at the standard normal distribution, and I'm going to say the data value minus the given mean divided by the standard deviation. And as we calculate that, I know I'll want to round to 2 decimal places. So 20 minus 9, we'll get that's 11 divided by 6, and that will round. Okay, we get 1.833 continuing. Look at the second decimal place right here at the 3. 1 past it is also a 3. That's less than 5, so we stay the same. So that's going to round to 1.83. And now we'll bring up our chart. We've got a z-score of 1.83, so we scroll to the positive values. We find what's aligned with 1.8. And we see from the chart for a z-score of 1.83, 0.9644 of the area lies before that, so that aligns with our less than 20. So that's our answer here. Now let's just talk through why this works. We began with a normal population, not standard normal. So at the beginning, we could not use this chart because that only works for standard normal. However, we have this new tool called the z-score that allows you to transform any normal into a standard normal. So we took our value of 20 that we were interested in, and by using the formula, we transformed it into a z-score. So now this 1.83 represents a proportional location in the standard normal curve, as 20 does in this normal curve with the mean of 9 and standard deviation of 6. Then using the chart, much like we talked about in detail in our last lesson, we found the area under the curve for values less than this is 0.9664. Well, the area under the curve is the same idea as the proportion of the population. Area under the curve, proportion of population, probability, all those are the same. So now as we look at our next example, what's the probability that a randomly chosen value will be greater than 5? So 5 here is now taking the place of our new x value of interest. However, I want to be cautious here. Do you see between A and B, A said less than 20, which is a perfect setup for using our chart because our chart tells us values area less than the point of that we're interested in. Whereas now it's saying greater than 5. I know the chart doesn't directly tell me about greater than. Instead, I could find the less than 5 and then take that away from 1. The details of why that works was talked about in detail in the last video in this series, but let's sketch that out here. So our strategy will be find the probability less than 5 and subtract from 1. However, 5 itself is a normal value, so we need to first transform it into standard normal. We take the x value minus the mean, divide it by the standard deviation, and we get -4 divided by 6. Let's type this into the calculator, and remember we round to 2 decimal places for our z-scores. And we type this into the calculator, we get 0.666 repeating. That would round to 2 decimal places. Excuse me, -0.666 repeating. And that rounds to -0.67 as the z-score. Once we have the z-score, we can then go to the chart. And keep in mind, the chart value will give you the area to the left, or the probability that we're less than the z-score of -0.67. We then subtract that value from 1 to get the probability that we would then be greater than. So we'll go to the chart and look up the z-score of -0.67. And we see that would be 0.2514. Now that is the probability that we're less than a z of -0.67 or an x value of 5. We cared about really being greater than that. We know that the value less plus the value greater must be 1. So the probability that we're greater than that is 1 minus the less than value of 0.2514. So our next example tells us that we've got our normal population. We know the mean, mu is 56. Standard deviation, sigma is 8. Notice they did not give us an x value here. Now if we're going to use our z-score, it is x minus mu divided by sigma, so we're missing that key detail. Instead of that detail, they tell us or ask us, what is the 85th percentile of the population? Now, a percentile means if you score this, you are greater than 85% of the population. So 85% of the population scores less than you. This percentile can immediately be translated into a probability in our standard normal curve. It's saying, what does the z-score have to be such that everything before it accounts for 85% of the population? Equivalently, the area under that curve is 0.85. So whenever you're asked to